not only is like nanomaterials itself this brand new thing, but then you get down to this, well, why this one? All the nanomaterials, like we get this idea, sheets, tubes, it's gonna work, it's gonna be this interesting thing. But then we have this obscure material that shouldn't work based on all of those things that we
You
just discussed, but
you're
it
at, but
does.
you're actually describing the history of nanomaterials because the thing is that people said that graphene couldn't exist. The
Ah,
computational people said that graphene physically, thermodynamically, everything, looking at backwards, forwards, it could never exist. If you made a single sheet of or of graphene, it would instantaneously crumble in on itself, like that it should be
ah,
completely unstable. And it wasn't until the lads in Manchester isolated it that everyone just went, oh yeah, I guess they were wrong. So it's just it is kind of one of those things that it's just like those kind of like computational assumptions actually nearly like stunted the nanoscience revolution, I guess, or kind of the field is that if
right.
people believe that it's just like, okay, maybe the computation people are right, let's not bother explaining graphene at all, then it's just like we wouldn't be where we are today.
Right. So it's like, yeah, don't always trust the modeling nerds. But do we do we do we know then where the flaw in the model was?
I think it's just
Like,
always with kind of modeling is that it's just like it is only as good as the experimental data. And I think it's just like if it
right.
doesn't match the experimental data, then you need to adjust the modeling if the experimental data if there's no obvious flaws with that. So it's just like I think it was just one of those things that I think the data wasn't there. So
Hmm.
there was just I guess the need for modifying the data was just I don't know, I guess it kind of seemed like maybe just it wasn't there wasn't any points.
Right, right. Yeah, I mean, it's kind of a weird, like really sort of probably like technical question, but it just seems like one of those things is like, yeah, if all the theory, again, it kind of makes me think of that quantum stuff, right? Where it's like all the equations say one thing, but when you get down to this thinness, this realm, it's like the rules change,
It actually
and
isn't that, it wasn't that actually difficult or even kind of technical. All it had to do was the fact that the theory stuff didn't compensate for the size of the materials. That was it.
mm,
Is that when the materials, their electronic properties were actually not only dependent on the number of layers they have, but also the size. So when they started to get really, really small, they started to look like insulators again. So they started to look like they're bulk materials. And all the computational models can only assume small nanosheets. So that's where we saw the discrepancy is that because they assumed that they were always, or they could only model them being small, that they always had these effects that made the band gaps appear large. Whereas because we could do it experimentally, you could control the size, we saw that as you changed the size, the actual areal size of nanosheets, that also changed the band gap size. And
interesting.
that was it. It was like it turned out to kind of just be something very simple, but it's just the fact that like just no one looked at it, and it can always turn out to be something just as simple as that. It was just literally just they just weren't thinking about the actual size. They were looking at the layers, but they just weren't looking at the actual size you could actually get. And that's why the initial people they got all these fantastical results because when they were making their nanosheets, they were massive, they're absolutely huge, and they were able to get them so thin, and that's why they were able to get these fantastic electronic properties. But yeah, it's like when other people did the modeling, they were like, "No, we don't see this at all." And it's like you need to think about their nanosheets were huge. Yours, you're assuming very small. So that was literally it. It was as
Wow.
simple as that.
This is like, okay, so a bit of an aside, but this is something that I talk about a lot is like, this need for the argument or the case for basic research, right? And like this feels like one of those things where it's like if someone doesn't just try it or like ask the question, right? You could do all the models could say all this stuff, and so you might, but if someone until someone just actually does it, you don't know. And I think that I'm going to make a point again here for like, this is why you do basic research, right? This is why you read somebody's paper and you say, oh, they did that. Interesting. What if we try it this way or something like that? And I feel like
Yeah.
there's so many, you got the politicians and the public that are like, well, why are we funding all this stuff, right? So there's a lack of understanding there. But then even just within the science community, people get so siloed, right? They get so focused on their one thing that they don't sort of look to other fields and see how, serendipitous discoveries or cross pollination of knowledge, all that kind of stuff goes on. maybe you have a thought on this, but this is something that I think about a lot as like science communication, because we often scientists think about, wow, we got to communicate to the public and we got to justify what we do. So this is a good justification for that. But there's also this interdisciplinary communication that I feel is lacking. And you probably would lose some of these interesting discoveries, or someone's going to take what you found and do something interesting with it. So,
I think a lot of it is just probably the kind of the mentality in academia that it's just I think when people kind of feel that someone's like has a question about their work, I think it's always kind of like interpreted as being kind of negative, or that you kind of need
mm,
to feel like defensive and I need to kind of justify my work. And I think, yeah, a lot of that kind of conversational aspect of academia kind of goes it's just kind of just gone away. I'm not sure if it was ever there. I think it might have to do with just kind of just the modes in which we publish. Is that you have anonymous reviewers, and they can sometimes be very critical or negative, and sometimes rightfully so, sometimes just overly critical for I don't know their competitor or something. And I think it's just I don't know, it's just a negative mentality because I mean what I kind of like think of things is that like people always go like, oh, like an industry person or something like, who's your biggest competitor? And it's like I don't see research like that, and I don't think people should. Like I'm not trying to compete against someone to do something. It's just like everyone is potentially collaborators. It's just like if there's someone else working on something just like I am, they're working the same thing. I'd rather reach out to them and be like, "What are you doing? We're doing this." And it's just like, we're getting this wrong, and I see you're getting this wrong. Like we could work together on this. Like I see, like there's more benefit to that than kind of just being like, "Oh, I don't like you because you do the same thing as me, so you're a
mm-hmm.
competitor, and I'm never going to talk to you." It's just like, well, that person could be an expert, expert in the field, and it's just like you're missing on this. Yeah, as you said, cross pollination, this knowledge, this kind of expansion that's just like this is how we'll get to this like next technological era. It's just like we need to stop being so damn competitive.